Welcome, everyone. We're going to cover today what we were supposed to do before the alarm went off. And where we were going to look is we were going to kind of pick up where we had left off last time, continue with the gradient, and we're going to look at the three variable case. So that's what we're going to pick up, see how to do the directional derivative for the three variable cases or three-dimensional case as well. And right away, let's start with the definition. So we define the directional derivative of a scalar function at a three-dimensional point, so x0, y0, z0, in the direction of a unit vector, again, with three coordinates there. And the directional derivative, we use similar notation, so it's the derivative in the direction of vector u. And it's defined very similar to what we saw in the two-dimensional case, so the same limit as h goes to 0. And this time we're letting x change, the x component change by a little bit in the direction of our unit vector. We're letting the y component change by a little bit in the as specified by our unit vector. And then we're letting the z component change by a little bit as specified by our unit vector. And we're seeing how this function, how the changes in this function, what happens as h goes to 0. So as those small changes go to 0. So we end up with this similar definition to what we saw in the two-dimensional case. And it ends up being important to look at the gradient of this scalar function. And we define the gradient very similar. So this is the gradient for our scalar valued function. And it's defined just like the two-dimensional case. The first component is the x partial derivative. Second component is the y partial derivative. And then now we have a third component, the z component, and it's the z partial derivative. And it's important to note the gradient is a vector. So we mentioned it last time. Let's mention it again. And to really emphasize that this is a vector, this is a boldface delta or a del, and it's hard to write boldface, so put the little arrow above just to really help us remember that this is actually a vector. And so we've just extended this for the three-dimensional case, and we can calculate the directional derivative very similar to what we saw in the two-dimensional case. We do our gradient, dot product with the unit vector. So when we do this, again, it's important. This is the dot product. And we need this to be a unit vector. So we need u, the direction that we're going to travel in, to be a unit vector. And the fact that it's a unit vector is important because we don't want the actual size of this vector to influence our derivative. So the size of this vector is 1. So all of the change that we're going to see is due purely to our function little f, not the actual vector, the size of the vector. All right, so let's try an example in the three variable case here. So we have this function f of x, y, z, and it's the function x times sine of yz, and we're going to find the gradient of this scalar valued function first. So let's calculate the gradient. And again, it's in the first spot, it's going to be our x partial. In the second spot, it's going to be our y partial. And then now in the third spot, it's going to be our z partial. So let's calculate all of those. So if we do the x partial derivative of x is going to be 1. And then the sine of yz is just like a constant multiple that's attached. So our x partial derivative is going to be sine of yz. All right, so now we got to get to our y partial derivative. So here the x is a constant multiple, and we see a y in this trig term. So we're going to have to differentiate our way through that trig term using chain rule. So first of all, the x is going to stay in front. Derivative of sine is cosine. We keep the inner function exactly the same, so that's going to stay a y times z. And this is there's an outer function and an inner function. So when we differentiate, we also have to multiply by the derivative of the inner function. So in this case, if we're looking at that inner function, the derivative of y is 1, and then the z is a constant multiple, so that kind of sticks around in our derivative. And we could write the times z over here, but I'm actually going to put it in front of the cosine, just to make it look nice. So we have x times z times cosine of yz. And then for our last one, we got to do the z partial. So again, the z is inside that trig function, so we have to use chain rule to break our way through that trig function. So the x is like a constant multiple. We're going to differentiate sine, so we're going to get cosine there. Keep the inner function exactly as is. And then we have to multiply by the derivative of what was inside. That's chain rule. So we're going to differentiate the yz term, but now we're differentiating with respect to z. So the derivative of z is 1, and then we're still going to have that y multiple left. And, like before, we could write it over here, but it's going to be neater to write it in front. So we'll write that in front there. And there's our gradient. So we have the gradient of our scalar function f. All right, so now let's actually get the directional derivative for this function at this point 1, 3, 0. So let's try this out. And we're going to find the directional derivative in the direction of this vector v, which has components 1, 2, -1. All right, so first of all, there's kind of two things we have to do before we actually calculate the directional derivative. We have to figure out the value of our gradient at our point. So let's start with that. So wherever I see an x in my gradient here, I'm going to plug in 1. Wherever I see a y, I'm going to plug in 3. And then wherever I see a z, I'm going to plug in 0. So when we do this, we end up with the vector sine of 3 times 0, so sine of 0. Then in the second spot here, we have z equals, well, we're going to plug 0 in for z, so that's going to eliminate that whole second term. So our second component there will be 0. And then down in our last component, we're plugging in 1 in for x, 3 in for y, and then 0 in for z. So we're going to end up with 3 times cosine 0. And just in case, at this point we really should be starting to have these values memorized. But sine of 0 is 0, cosine of 0 is 1. So we end up with the vector 0, 0, 3. All right, so that's our gradient vector. Now we have to find our unit vector. So that's kind of like step 1. Step 2, we need our unit vector. And we have the vector that's telling us the direction, but right now this isn't a unit vector because its length isn't 1. So we gotta make it. We gotta construct a unit vector. And the way to do that, this is something we've seen before, is you figure out the length of the vector you're interested in. So we're going to figure out the length of vector v, and we're going to essentially multiply each component of vector v by the 1 over the length. Or another way to think of this, take your vector v and divide by the length. All right, so if we go up to vector v, we're going to calculate the length of this thing. And so we square each component. And what we end up with is 1 plus 4 plus 1. And then all of that goes under the square root. So our length of vector v is is square root 6. So our unit vector is going to be our vector v times 1 over that length. Or if we wanted to, we could distribute this and essentially divide each component by square root 6. Perfectly fine to do it like that. Sometimes I think it's a little easier to keep that factored out in front. Any common factors, so that way your vector itself is a little bit easier, but either way is fine. And so now that we have our gradient vector figured out, our unit vector figured out, we want to calculate their dot product. And that's going to give us the directional derivative. So that's the last part of this. We're going to get our directional derivative at this specific point in the direction of this unit vector. And so if we plug in what we have, it's going to be the gradient of vector f evaluated at this point, dot product with our vector u. And let's fill it in. So our gradient we said was 0, 0, 3. And we're going to do the dot product with our unit vector. And I'm leaving a little space here because I'm going to take this scalar multiple that's in front of vector v, and I'm actually just going to put it in front. And then I'm just going to use the vector component from vector v. So 1, 2, negative 1. So we can do that, dot product. If we have a scalar multiple, we can essentially factor that scalar multiple out in front of the dot product there. And then sometimes I think it's a little easier to do that. And then to do the dot product, just multiply across, and we get 0 plus 0 plus negative 3. So we get negative 3, and then we have our scalar term in front. So we end up with negative 3 over square root 6. And that's our directional derivative. All right, so this gradient gadget we're going to see is actually pretty important. And one of the kind of the important properties of it is that it gives us information about where our directional derivative is a maximum. So we have this result that says, let's suppose f is a differentiable function of 2 or 3 variables, what we're going to be calculating. And it says the max value of the directional derivative. So this directional derivative at a specific point. So imagine we're standing at a specific point and we want to know where is their function changing the most, or what is the fastest our function is changing. So that max change, that max value of our derivative is the length of our gradient vector at that point. And kind of more importantly, that max value actually happens when our unit vector is the same direction as our gradient at that point. So the gradient essentially is telling us which direction to go in where our function is the steepest, where it's changing the most. So that's the way you want to think of how this gradient works, is the gradient is telling us the direction, is kind of the steepest direction we can travel in. At a specific point. So imagine standing on your surface and you have the full kind of circle of directions to go in. Well, this specific direction, the gradient of our function, is kind of the steepest direction you can travel in. So let's actually, the proof for this actually isn't too bad, and it relies on just a little bit of knowledge about what the dot product is and what, a property of cosine. So let's look at the proof of this. So our directional derivative of a scalar valued function is, as we've seen, the gradient of the function dot product with our unit vector u. And we've seen this. These are 2 vectors. And when we do the dot product of 2 vectors, another way to calculate the dot product is it's the length of the first vector, just regular multiplication now, times the length of our unit vector, times cosine of theta, where theta is the angle in between those 2 vectors. And this is just the definition of dot product of two vectors. We have one vector, dot product with another. It's the length of the first one times the length of the second one times cosine of the angle that sits in between those two. Now the property, now the length of vector u here, well, u is a unit vector. So this is just one. Kind of by design. This was just a unit vector. So actually, this directional derivative is the length of our gradient vector times cosine of theta, where again, theta is the angle in between our unit vector and the gradient vector. Now, if we look at this, cosine of theta has certain properties. So cosine of theta is any angle is somewhere in between -1 and +1. And so the max, the largest value this can take is when cosine of theta is equal to 1. That's the largest value cosine theta is ever going to be. So the max value occurs when cosine of theta is equal to 1. Now, if cosine of theta is equal to 1, we know what value of theta makes that true. That's theta equal to 0. So if theta is equal to 0, that means u and the gradient are pointing in the same direction. So they might have different lengths, but they're both pointing in the same direction. So what this is telling us is that the largest this directional derivative ever gets is when cosine of theta is equal to 1, and the value that happens there is this length of our gradient vector. And that also happens when the gradient vector and our direction they're going in the same direction. So u and the gradient have the same direction. So the max value of our directional derivative is the length, and the direction it happens is the gradient. So kind of interesting. And we're going to see more of this in a little bit. So let's try an example, though. So we have the scalar valued function here. So it's a two-variable function, f of x, y, and it's x e to the y. And we want to find the rate of change of our function f at this point, p, with coordinates 2, 0. And we want to go in the direction from p to point q with coordinates 1, 1/2, 2. All right, so we see this wording rate of change. So immediately we're thinking derivative, but now we're going in a specific direction, so we're doing a directional derivative. So there's a few things we need. First thing, let's get the gradient. So let's calculate our gradient evaluated at this specific point. And that means, well, let's get the gradient function first. So let's calculate the gradient of this function. So again, we're in the two-variable case, so it's f partial x, f partial y. That's it. And if we go up to our function here, let's get f partial x first. So the derivative of x is 1, and then e to the y is just a constant multiple. So we're going to have e to the power y as our first component. And then for our y partial derivative, e to the y, the derivative of e to the y is just e to the y, and x is a constant multiple, so it just sticks around. So our y partial derivative is actually the exact same as our function, x e to the y. And so now, to actually evaluate this, we're going to plug 2 in for x and 0 in for y. So when we plug 0 in for y, we're going to get e to the 0, which is just 1. And then we'll have a 2 there for x. So we end up with the vector 1, 2 once we plug in. All right, so next we're going to need our unit vector. And we're told that we're going to go in the direction of PQ. So we're told that we're actually looking at our direction vector is kind of given by the vector PQ. Now this is probably not going to be a unit vector. Maybe it will, but we're going to see it's actually not. So once we get PQ, then we're going to have to make it into a unit vector. All right, so let's calculate this vector PQ. So we take the end point and we subtract off the starting point. So if we do that, we end up with -3/2 and then 2 minus 0. So again, we're taking 1/2 minus 2 and then 2 minus 0 to get our components there. And now we got to make this into a unit vector. So the quick way to do this is to figure out the length of your vector PQ and then multiply that, do 1 over the length and then multiply it into the vector there. All right, so what do we get for the length of this vector that we calculated? Well, if we square the first component, we get 9 over 4. And then if we square the second component, we get 4. And we want to add these together. So we have 9 over 4. Let's write that other one as 16 over 4. So we end up with the square root of 25 over 4 as the length. 9 plus 16 is 25. And that ends up just being 5 over 2. So we end up with 5 over 2 as our length. And then if we throw in our vector here, and then we just want to simplify this down. So if I clean this up, we're going to end up with -3 over 5 for our first component, and then we're going to end up with 4 over 5 as our second component. And if I wanted to, I could factor out a 1 over 5 there, just to make it a little easier. All right, so we have all the pieces now. So we have our gradient vector at the point. We have our unit directional vector. So now we're ready to actually calculate the directional derivative. And that's the last step here. So we're going to calculate the directional derivative at this point by using the gradient at the point, dot product with our unit vector. So if we fill in what we found that the gradient was 1, 2, the point 1, 2, and our unit vector was -3 over 5 and 4 over 5. And we multiply across and add up the results to do the dot product, and we end up with -3 over 5 plus 8 over 5, which ends up being 1. And so that's our directional derivative. So what this is telling us, if we were standing on our surface at this point 2, 0, and were to take a small step in this direction, kind of figure out where that direction vector is, and then take a small step in that direction, the height of our surface would actually increase by 1 there. Okay. So that's the directional derivative. And then for part 2 of this one, in what direction does f have its maximum rate of change? And then what is that maximum rate of change? So first of all, the direction of our max rate is going to be the gradient by that previous result. So it's just the gradient at this specific point. And we said that that was the vector 1, 2. So this vector is where if we take a step in that, figure out where that is, and then take a step, that's going to be where our surface is the steepest. And what is the max rate of change? So the actual rate of change is the length of our gradient vector at this specific point. So we want to calculate the length of this vector 1, 2. And if we do that, square the first component, square the second component, add them up, we get 5, and then do the square root. So this ends up being square root 5. So this is the direction where the kind of the surface is the steepest, and it'd help if you could see it. And this is how steep the curve of the surface is in that specific direction. And this is the kind of the max rate of change. The max, again, think of this as like a slope of the tangent line. So if we kind of take a step in that direction, we're really finding the slope of the tangent line in that specific direction. And this is as big as it gets. All right. So let's try another one. Example 6. We're going to look at a kind of a 3-variable case now, but the same idea holds. And for this one, we're going to be looking at a temperature function. So our temperature function here, we'll call it T for temperature. And it's 80 divided by 1 plus x squared plus 2y squared plus 3z squared. And we're measuring the temperature here in Celsius. And these x, y, and z positions are being measured in meters. All right, so let's get the gradient of this temperature function. So let's start with that. And there's going to be a little work here, not too bad, but let's start with the x partial derivative of our temperature function. So what we're going to do is let's rewrite this function. I'm going to rewrite it as, instead of 80 divided by, so instead of having division here, we'll have to use quotient rule and all that. Let's write this with a negative exponent. So I'm going to rewrite this as 80 times 1 plus x squared plus 2y squared plus 3z squared. Raised to the negative 1. So sometimes using a negative exponent here, it's just a little easier. That way we don't have to use quotient rule once we get the derivative. And we're going to we're going to differentiate with respect to x. So we're going to do the x partial here. All right, so how is this going to work? Well, we're going to use our chain rule. We're going to use the general power rule that says, take this exponent, bring it down, multiply it with the 80. So we're going to end up with negative 80 in front. Then you keep what's inside the parentheses exactly the same. And then we subtract 1 from the exponent. So we go from negative 1 down to negative 2. And that's not it. Then we need to take everything that was inside the parentheses and multiply by the derivative. Now in this case, we want to multiply by the partial derivative of everything inside with respect to x. So that's what we're going to put over here. So we want to figure out what is the partial derivative with respect to x of everything that was inside the parentheses. And if we do this, derivative of 1 is 0. The derivative of the y term here is 0. And then same thing for the z term. The derivative of that is going to be 0. The only contribution we're going to get is from this x squared, which gives us 2x. So that's the x partial for what was inside. And similar for the y partial. So for the y partial, this power rule part is going to be exactly the same. No change. So we're going to end up with a negative 80 in front. Keep what was inside the parentheses exactly the same. Subtract 1 in the exponent. And now the only thing that's going to be different is what do we multiply by when we do the derivative of what was inside with respect to y? So in this case, if we look at our inner function, and the derivative of 1 is going to be 0. Derivative of x squared is going to be 0. And then derivative of the 2y squared, that's going to be 4y. And then the derivative of the z term is 0. So 4y is the only piece that we get by doing the partial with respect to y for that inner part. And then same thing for z. So if we look at our z partial, again, the negative 80 is going to be there. We're still going to have the 1 plus x squared plus 2y squared plus 3z squared, all that inner function, still going to be negative 2. And now we just have to multiply by the partial derivative of what was inside. And the partial derivative of what was inside with respect to z, the only contribution we're going to get is from that last term. And that's going to be 6z. All right, so if we look at this, let's kind of simplify this gradient. And there's certain things that we can actually factor out. So we're doing the gradient of the t function here. And if we look, there's certain pieces of these partial derivatives that show up in all three of them. So all of them have this negative 80 in front. So we're going to be able to factor that out. All of them have this raised to the negative 2 function. So we're going to be able to factor that out. And then actually, all of them have a factor of 2 that we'll be able to factor out as well. So what we're going to be able to factor out is a 2, a negative 80. So let's write that as negative 160. And then this whole piece raised to the negative 2. And rather than raised to a negative number, let's write it back as a fraction. So we'll write it as 1 plus x squared plus 2y squared plus 3z squared raised to the negative 2. All right, so we were able to factor that out, that kind of scalar piece from all of these partial derivatives. And what we have left is from the x partial, we're just going to have x. From our y partial, there's still a 2 here, so it'll be 2 times y. And then from our z partial, there's still a 3 here, so we'll have 3 times z. So it's not necessary to factor all this out. We could have just written a vector with these 3 components, but it's helpful to factor out. Try and factor out as much as you can so we can see kind of the important vector part here. All right, so for part B, so we calculated the gradient. We got it all nice and factored and kind of tidied up. But now for part B here, we want to know in which direction does this temperature function increase the fastest at the point 1, 1, negative 2. So we want to know where is the temperature changing the fastest. That's talking about a derivative. And we're looking for a derivative, so we're interested in the directional derivative. And we know by that result that where the change happens the fastest is given by our gradient. So we want to look at the gradient evaluated at this specific point. So let's calculate this. So we want to plug the point 1, what was it? The point 1, 1, negative 2 in. So wherever I see an x, I'm going to plug in 1. Wherever I see a y, I'm going to plug in 1. And then wherever I see a z, I'm going to plug in negative 2. So for this kind of vector portion here, I'm going to get 1, 2, negative 6. All right. Now what about that whole big term in front? So that whole big piece in front here, again, I'm going to evaluate. So I'm going to plug 1 in for x. I'm going to plug 2 in for y. And then, 1 in for y. And then negative 2 in for z. So when we do that, we're going to end up with negative 180, or 160, divided by 1 plus 1 plus 2 plus, negative 6 squared. Right, let's get a little more room. So we're going to, when we plug in, we're going to get 1 plus 1 squared plus 2 times 1 squared plus 3 times negative 2 squared, and then that whole thing squared. And then our vector we said was 1, 2, negative 6. All right, so this is our gradient. Let's see what this simplifies to. So if we kind of work with the denominator, this is going to be 1 plus 2 plus 12. That ends up being 16 down in the denominator there. So we end up with 16 squared, which is 256. And then we're multiplying that with our vector 1, 2, negative 6. All right, so that's our gradient. Now, it's asking us for the direction. Now, we could use this whole thing perfectly fine. But it's not asking for a unit direction. It only wants just a direction. So we could just use the vector component of this, just to make it a little bit easier to read. So the direction of our max rate of change here is just going to be this vector part, not the scalar portion, with one exception, and that is we need that negative, because that negative actually is telling us part of the direction. So let's bring that negative, it's important, let's bring it inside the vector here. So the direction of our max rate of change is going to be the vector negative 2, negative 1, negative 2, positive 6. We also would have been perfectly fine just leaving it like this. So either way. And then for the third part, what is the maximum rate of increase? Well, the maximum rate of increase of our function then, we need to get the length of our gradient vector. So the max rate of change is equal to the length of our gradient vector at this specific point. So we want to calculate the length of our gradient. And for this one, we can't just use any direction vector. We have to actually use what the gradient actually was. And so, again, it kind of helps to have it factored out like this, because what we can do is we can do the absolute value of the scalar part that we factored out, and then just figure out the length of this other vector. So a way to kind of think of this is we can do the absolute value of negative 160 over 256, and then multiply that by the length of the vector 1, 2, negative 6. So sometimes this might be a little easier if you're able to factor out those numbers. And so this vector, it's not too bad. We square everything up and add it and put it under the square root sign. So 1 plus 4 plus 36, add that up, we get 41. So the length of this vector is square root 41. So we end up with 160 over 256 times square root 41. And we're doing the derivative of this vector t, or this function t. So the units for vector t are degrees Celsius here. And we're doing a kind of a directional derivative, so it's divided by the units of our x, y, and z coordinates. So in this case, meters. So this is telling us that if we were to take a step in this one particular direction, our temperature function is going to increase at a rate of this value in terms of degrees Celsius per meter. All right, so this actually allows us, this gradient gadget gives us a kind of a way to kind of go back and revisit tangent planes. So we can define the tangent plane to a level surface where we have this equation that's giving us the level surface. So we have some function f of x, y, z equal to a constant k. And so if we have this level surface, we can find the tangent plane at a specific point. And the way our tangent plane's defined is it's the plane that goes through the point P, and the normal vector is actually given by the gradient. So if we kind of remember, let's recall, what is the equation of a plane? Well, in general, it's the normal vector dot product with our general position vector minus the specific position vector of our point. So we call that R0, and we set this equal to 0. So what the tangent plane is, the normal vector is the gradient. So this is just the general equation for a plane. This is what we've looked at, we've been looking at all along here. What we're seeing with the tangent plane is we can view this as the gradient of our function capital F. And we're doing the dot product with the general position function r. And let's write what r actually was. So that's where we had x, y, and z. And then r0, that's the actual vector given by our point, our position vector. So that's x0, y0, z0. And we set this equal to 0. And so if we actually calculate this and work it out, remember the gradient is the x partial, y partial, and the z partial. And so if we do that dot product, we end up with the x partial derivative times x minus x0. We get the y partial derivative times y minus y0. And then we get the z partial derivative times z minus z0. And this is all equal to 0. All equal to 0 there. So, I think it's helpful to remember that, maybe this vector equation, there's a little bit less there. And the only thing to remember then for our tangent plane is that the normal vector is given by the gradient. So not too bad. And so this allows us to think of tangent planes to not just level surfaces, but maybe implicitly defined functions. So we can also use this if we have an implicitly defined function. So this gives us a way to get the tangent plane if we're maybe viewing z implicitly as a function of x and y, or maybe we're viewing y implicitly as a function of x and z. Depends. So we're still able to calculate. So even if we don't have actually what z is equal to, we're able to still figure out the tangent plane. All right, so let's kind of look at a little example of what's going on. A little graph here. And so here is a surface. So we have our level surface. This is given by some function f of x, y, z equal to a constant k. And a way to think of the surface, a level surface, ooh, excuse me. If we're thinking, it helps to think of it in terms of like a temperature function. So especially when we're talking about 3 variables here. So what we're doing is with a level surface for a 3 variable function, you want to think of all the points that sit on this surface here. They all would have the same temperature. So all of the points on this surface all have the same temperature. All right, so that's our level surface. And then we're looking at a specific point here. So here's our point P. And then that vector that's kind of pointing out away from the surface, that's our gradient. So that's going to be the gradient of this function capital F. And then we have our point, we'll call it point P there. All right, so what ends up happening is that if we were walking on this curve, if we were walking on this surface, so imagine we had a curve that sits on this surface and we go through this point P, any curve that goes through that point is going to have a tangent vector, and what ends up happening is that tangent vector is going to be orthogonal to the gradient. So imagine that we have a curve. Let me get a... So let's imagine that we have a curve here that goes through, we're walking on the surface and we go through that point. Well, what ends up happening is for that general curve, we're going to have a tangent vector. And let me get a different color there. So we're going to have a tangent vector. And that tangent vector is perpendicular. It's orthogonal to the gradient. And this is going to be true for any curve on this surface. So we have a curve, any curve, call it C, and then we have the tangent vector to this curve C. And so what ends up happening is the gradient is orthogonal to every tangent vector. Well, for any curve. So any curve that you want that's on the surface, the tangent vector at that point is going to be perpendicular to the gradient. So, and we'll revisit this in a little bit, but the gradient is kind of pointing away. It's pointing kind of away from our kind of flat changes, which is the tangent plane. So it's kind of telling us where the maximum change is going to happen. So if this was like the temperature function here, this is the direction where we would see the most change in our temperature. And so kind of a special case for this is the tangent plane formula we had seen before. So we had looked at tangent planes before when we specifically had an equation z equal to f of xy. And in this case, this is now, we're going to be able to view this really as a special case of this more general version. And the reason is because we can take this equation z equal to little f of xy, and we can rewrite this. And we can do this in the form of some function capital F, X, Y, Z equal to a constant K. And the way we can do this is by essentially moving the Z term over. So we end up with little f of xyz minus, or little f of xy minus z equal to 0. And what we can do is we can view this left-hand side as our function capital F. So we're going to use capital F of xyz equal to little f of xy minus z. And so if we want to find the tangent plane for this level curve, level surface, so this is going to give us a level surface. So it's some function of x, y, z set equal to a constant. So this is a level surface, and we're looking at a specific point. Well, let's actually see. So the tangent plane then is going to be the gradient of this function capital F dot product with the vector x minus x0, y minus y0, and z minus z0, all set equal to 0. And let's actually figure out what the gradient of this function actually is. So our gradient, we want to start with the x partial derivative. So the x partial derivative of the first term is just going to be f partial x. And then there's no x term here, so that's going to be 0. So it's going to be little f partial x. And then what about the partial derivative of this function capital F with respect to y? Well, it's going to be the partial derivative of little f with respect to y. And then there's no y term here, so that's just going to be 0. And then when we do the partial derivative of this with respect to z, well, there's no z term here, so that's just going to be 0. But we are going to get a minus 1 from here. And so if we look at this dot product set equal to 0, what are we going to get? We're going to get the x partial times x minus x0, the y partial times y minus y0, and then -1 times z minus z0. And that's precisely what we end up with. F partial x times x minus x0, f partial y, y minus y0, and then we just end up with z minus z0, and we've just moved it over to the other side so that we don't have the negative. So this gives us a way, if we have a kind of a function capital Fxy that's written as a level curve set equal to a constant k, well, we're able to figure out the tangent line. So the tangent line formula we've seen before, it's kind of a special case now for this gradient version. And with our tangent line, we're able to define the normal line. So if we have a level surface, so some function f of x, y, z set equal to a constant k, we're able to find the normal line. And this is just the line that goes through point P and has the direction vector equal to the gradient. And if we remember, let's recall, what is the formula for a line? Well, the parametric formula for a line is r of t is equal to the position vector of our point plus t times the direction vector. And now we're saying the direction vector here is actually given by the gradient. So this is the gradient of our function capital F. And then R0 is still just the position vector of our point. So this is just the formula for a parametric line equation. Well, if we wrote it out, this is actually the vector formula. But we could easily think of this as vector xyz, and then x0 is x0, y0, z0. So that's our general position. And then our vector v, our direction vector, is the gradient. So let's actually write out what that is. So we'd have plus t, our parameter, times the x partial, the y partial, and then the z partial. So that's telling us the direction, and then we have our specific point. And if we want, we could write that as in symmetric form. Probably generally it's easier to use parametric and vector equations, though. All right, so we're going to skip over example 7. But I do just want to mention the significance of the gradient vector here. And I think it's a little easier to picture for the two-variable case here, the two-dimensional case. And so what we've seen is that the gradient for a function represents the kind of the steepest direction to travel in at a specific point. And let's kind of view this in the two-dimensional case. So let's say we have a specific point P here, and let's say that we have a level curve. And we're in the two-dimensional case. So let's say this is just little f of xy equal to some constant k. So here's our level curve. So what that means, if we're looking at thinking of this as like a two-dimensional function, f of xy, you could think of all these points on this curve as all having the same height. And so, again, kind of think of like a contour map. So if we have a contour map, all the contours, these are all level curves. All these points on these contour lines have the same height. Okay, so that's what this is. This is a contour line right here. And we've seen that if we have a contour line, we can figure out the tangent line to that contour. So we have our tangent line at point P. And so imagine standing on our surface, and what the tangent line tells us is the tangent line is telling us which directions to go in, where the change in height is going to be 0. So that's what the tangent line tells us. The tangent line, or the tangent vector, is telling us the direction where the change in height is 0. So that's why if you're ever like hiking a mountain and you want to take it easy on yourself, what you're going to do is, rather than walking straight uphill, you could walk along the contour, and you're not actually walking uphill or downhill. You're just walking flat. Your elevation isn't changing. So there's no vertical gain there. So you can just walk along the contour line there. And that's what the tangent line is telling us, is that if we're at this point and we kind of if we walk at this specific point, if we walk in that direction, our change in height is going to be 0. What the gradient does, though, so what the gradient of our function little f does, this is now perpendicular. It's orthogonal to our tangent line. And so the tangent line is telling us which direction to go in, where our change in height is going to be 0. The gradient is actually telling us the direction where it's going to be steepest for us to travel in. All right, so it makes sense then that if we kind of think of it like this, the tangent line is telling us kind of the directions where the change in our height is going to be 0. So it makes sense then that where we would have the greatest change happens in between those kind of two end caps. So if we're standing at this point, we have all these different directions to look at. And so where our change is going to be the kind of the least in terms of increasing or decreasing, that's going to be along the tangent line. And so it makes sense then, almost right in the middle there, that's where our gradient is, and that's where we're going to have the biggest change. So just to kind of end this with a contour, going back to our contour map here that we've seen before, we can kind of take a path of steepest ascent or descent. So again, let's kind of imagine we're standing at a point, and we can take what's called the path of steepest ascent. So as a little example, let's imagine that we're standing here, and we can, if we wanted to kind of travel in the steepest direction, what we would do is we would start moving so that we're always moving perpendicular to these contour lines. So if we're at this point, we walk a little bit, it's perpendicular to our contour line. Then we keep going, and again, perpendicular to our contour line. Then we go a little bit more, perpendicular to our contour line. So we're always trying to walk straight up the hill, basically. So we're not moving parallel to a contour line, because then we'd be staying flat. What we're always trying to do is we're trying to go perpendicular to the contours, the level curves here. And so we get what's called a path of steepest ascent, and we can kind of use this then to help us find where we might have a maximum. Well, we can work our way up the mountain that way. So as we're going, trying to get all of these make them look perpendicular, but we keep going, and eventually we make it our way up. But the path of steepest ascent happens when we're always moving perpendicular to the contour lines, and that's the direction our gradient is telling us to go. So the gradient is telling us where to go so that we're always moving perpendicular to the contour lines. All right, so we're gonna stop there. So that was what we had covered in the previous class. So that's what I wanted to get to. And all right, so we will see you on Monday. Hopefully no more alarms. So have a nice weekend, and we'll see you on Monday. Bye-bye.